Good morning, everyone. My name is Rafael Romero Méndez, and I'm here to present my project on the propagation of quantum noise nonlinear fields in integrated photonic devices. I know that from a totally sales, there might be a lot of questions. So let's start by breaking down integrated photonic devices. These devices involve the fabrication of nanoscale photonic devices, such as lasers, waveguides, onto really small substrates, and we're speaking millimeter scale. Here I displayed some examples of integrated photonic devices. These devices allow us to create, control, and detect light particles or photons. But more importantly, these devices hold outstanding promise in modern technology. Here I have put some applications. However, the most important of them all is quantum metrology, which is the art of using quantum mechanical principles to improve or provide more precise measurements. This is the most recent example of light interferometer, in which it uses squeezers, which is a quantum optical device, to improve the sensitivity of their detectors. Now, when we measure or detect signals, sometimes there is unwanted information that we regard that as noise. For photons or light signals, we have something known as vacuum fluctuations, and that is because photons are a quantum mechanical object. This vacuum fluctuation is what we regard that as quantum noise. Now, it turns out that there's not a fully accurate quantum noise model up to this day. Furthermore, trying to simulate the dynamics of quantum noise is a huge computational task. That is because the Gilbert space size increases exponentially by the number of modes or light waves inside our devices. So, my project revolves on simulating quantum noise dynamics while also reducing computational resources. To do this, we use the high-performance computing cluster, SARC. Now, the way we study quantum noise is via quantum squeeze state, and I will illustrate this by the following example. Consider that we start with an initial laser pulse that we refer to as a coherent state, and only depends on amplitude and phase. And you can see from the signal, there's some noise associated with the signal. According to Heisenberg's uncertainty principle, for two non-commutative parameters, we may either know one very well, but not the other one, or vice versa. Now, we can use this as our advantage. Consider that in our signal, we do not care so much about amplitude, but we care about phase. So we can quite literally squeeze in phase by increasing the noise in the amplitude. This allows to have well-defined phase, but noisy amplitudes. But we don't care about amplitude, we care about phase. And we can do the other way around. We can have amplitude squeezing. This allows to do both study and reduce quantum noise. Here I display the Hamiltonians for the equations of motion that I will simulate. These Hamiltonians represent a straight linear, nonlinear waveguide. Now, the Hamiltonian essentially describes the entire energy of our systems. And we have divided this Hamiltonian into two different Hamiltonians. First is a nonlinear Hamiltonian that deals with nonlinear interactions, for example, four-way mixing. And the other one is the dispersion Hamiltonian. Now, when you look at the definition of our Hamiltonians, these produce nonlinear partial differential equations that depend on annihilation and creation operators. And it turns out that for this, we need numerical simulations. This is why we rely on the split-step Peter method, which is a simple concept. Imagine that this is just a straight waveguide, and we have divided the waveguide into a step of size h. And consider that during this region, we only consider dispersion. That is, our nonlinear operator is equal to 0. If we go with this assumption, essentially now this equation does have an analytical solution. Now, to account for nonlinearities, we essentially multiply our nonlinear operator as a perturbing factor. This is how we're able to solve the equations that I showed earlier. So we're ready to move on with our results. Here, first, I simulated a bright soliton going into a straight waveguide. I display here the input field, and the blue corresponds to the initial field, that is at the first time, and the orange corresponds to the final field, which is the last time. Now, note that for the bright soliton, the initial and the final fields are essentially the same. That is because by definition, a bright soliton is a perfect balance between nonlinearities and dispersion. Here I display the squeezing levels. Squeezing levels is just a visual way to represent how much noise has been reduced. Now, for each squeezing level, there is an associated combination of superposition of all the modes in our system that optimize or provide a better noise reduction. We call this supermodes. Something interesting to know is that these waveforms are essentially eigenvectors and solve our Hamiltonians or eigenstate. Now, from here we can have our first insight. You can see that the initial supermode, that is the first supermode, which corresponds to this blue curve, provides the best amount of squeezing. That is, these waveforms are the ones that provide more squeezing and thus more noise reduction compared to all other supermodes. And here I plotted the third supermode, but note that it's barely producing any noise reduction. Now, remember that I spoke about quantum squeeze state. We can visually see the squeeze states. And here I plotted the squeeze state at some times, and you can see that at the final time, our state has been really squeezed, which implies that we have indeed reduced noise. And here we have noise reduction of 4 times. For reference, we also simulated a Gaussian field. Now, note that the final field has indeed brought more than the initial field. This suggests that for a Gaussian beam, dispersion plays a bigger role than nonlinearities. Just like before, we have our squeezing levels and their associated supermodes. And just like before, the first supermodes are the ones that produce the more amount of squeeze. Now, note that for the Gaussian beam, we only have 2.5 times of noise reduction. And you can see from the squeeze states that even though they are squeezed, they're not as squeezed as the bright soliton, which leads us to our second insight. For experiment, it's better to use a bright soliton as it produces the less amount of noise, or another way to say it produces the most amount of squeezing than the Gaussian. In summary, here we simulated 2 initial fields in a linear waveguide. We have a bright soliton and a Gaussian beam. We also showed that it is possible to study and reduce quantum noise via quantum squeeze state. We also determined that the shapes of the initial pulse, or that is the supermodes, the first supermodes, to be more specific, affect the amount of squeezing, or that is the amount of noise reduction we have in our system. And we have two simulations. For a bright soliton, we obtain approximately 4 times of noise reduction, and for the Gaussian beam, we obtain 2.5 noise reduction, suggesting that it's better to use a bright soliton over a Gaussian beam. I would like to thank all the members of the Fluke Lab, as well as Dr. Daniel Serrano and Dr. Franz Klein. Thank you.